So first of all, I would like to thank the organizers for the invitation to this conference. So the results I would like to present to you today have been obtained in collaboration with several people, with Aurélien Grapsch, who was a postdoc in the group and just got a permanent position, Alexis Poncet and Pierre Escala, who have been PhD students, and my colleague and friend, Pierre Hélien. So these results concerns single file systems. So first, what are single file systems? So single file diffusion, as you know, refers to the motion of particles in narrow channels in which the geometrical constraints do not permit the particles to bypass each other. This is a very strong constraint and it has strong consequences. If, for instance, you follow the motion of a particle, in blue here, a tracer particle, its motion at long time is not diffusive, but subdiffusive, with a mean square displacement which is proportional to the square root of time t and not to t as for regular diffusion. This is an important theoretical result, and it has been observed in a variety of physical situations, including the motion of molecules in zeolites at larger scales, colloids in confined system, as was done in the group by Cumulance, and also a molecule of waters in nanotubes. So finally, tracer subdiffusion in single file systems is theoretically important and physically observed. A minimal model accounting for this single file diffusion is provided by the so-called Symmetric Exclusion Process. We already heard about it yesterday, but I just would like to remind you the definition of this process. So you consider particles on an infinite line. This is a discrete structure, one-dimensional lattice. This lattice is supposed to be initially populated by hardcore particles with a given density rho, meaning that a site initially is occupied with a probability rho. This is an annealed condition. And we assume that these particles perform symmetric continuous time random walks with the constraint that the site is occupied by at most one particle. And this is conveniently referred by the so-called occupation number at site R, equal to 1 if the site is occupied and 0 otherwise. So as you know, this is a very famous model of statistical physics. It has led to a huge number of works. I just would like to remind two important results concerning tracer diffusion. First, the mean square displacement. As a single file system, as we already know, it is proportional to the square root of time t, but you can, in addition, determine the prefactor, and in particular, its dependence on the density rho. Second point, because x is typically like t to the 1/4, you can be interested in the rescaled process, x rescaled by t to the 1/4, and it is known that this process converges to a Gaussian process, more precisely a fractional Brownian motion with an exponent 1/4. This is a very important result, but it does not give access to the full distribution of xt. In particular, it does not say anything about the cumulance beyond the second one. And this question, determining tracer diffusion in the SEP beyond the MSD, has attracted a lot of attention in the last decade. So more precisely, these higher cumulants, just remind you how they are defined. You start from exponential lambda xt. Lambda is the conjugated parameter of the tracer position xt. You take the average and the log. You expand this quantity as a function of the conjugated parameter lambda. By definition, the coefficients are the cumulants. Here, I will restrict myself to the case of a symmetric situation. All the odd cumulants will be equal to 0. Existing contributions can be schematically classified as follows. First class of results concern the so-called dense limit when rho goes to 1. This case is by far the simplest of all cases because technically you're back to a two-body problem just by counting the vacancy that interact with the tracer. You can show that all the cumulants, not only the second one, are proportional to square root of some t. Actually, this holds true for any density, not only for the dense limit. But in the dense limit, you can calculate very easily all the cumulants, and they assume this very simple form. You can also consider the opposite situation of a dilute system. Actually, this is more complicated, and there is a series of important works that have calculated all the cumulants in this situation, or equivalently, the large deviation function. Just a remark, This dilute limit of the set is important by itself, but also because it can be shown to be equivalent to the model of hard point-like Brownian particles on a continuous line. So this time, the system is continuous, not discrete anymore, and this is another example of single-file system. Finally, at arbitrary densities, there has been two very important works. First, the force cumulant at arbitrary density has been calculated by Paul and co-workers by using the so-called microscopic fluctuation theory. We heard about it in the talk of Pierre yesterday. And as you can see, the expression of kappa 4 is quite complicated, in particular, the dependency on the density. More recently, in 2017, there was a real breakthrough in the field. Imamura, Malik, and Sasamoto determined not only the force, but all the cumulants at arbitrary density. They obtained an exact parametric formula of the cumulant generating function by relying on the so-called integrable probabilities. So this is very important work. Oh, ugly. This is ugly, and this is a parametric expression. Okay, but in particular, you find back this kappa 4, and I will give other examples later of the cumulants you obtain. So this is implicit expression. So finally, the important point is that all the cumulants, not only the second one, behave anomalously for tracer diffusion in the SEP. Physically, it originates from the strong correlations involved in the single file geometry because the particles cannot cross each other. However, so far, there was no full quantitative determination of the Bass tracer correlations. Actually, this constitutes a real many-body problem, and this is exactly what I would like to discuss today. What can be said about these Bass tracer correlations, and is it possible to determine them explicitly, analytically? So more precisely, I will give some elements about the microscopic equations. I will then go to the hydrodynamic limit. I will consider first specific cases, as I mentioned for tracer diffusion, dense and dilute limits, before considering the general case and considering some possible extensions. So before giving the microscopic equations, I just would like to define in detail what I mean by correlations here. So to do that, let us try to imitate what we did for the tracer position xt. So we said that we were interested in the CGF, defined this way by introducing a conjugated parameter. When expanded as a function of this conjugated parameter, it defines the cumulants, and it is interesting to know the scaling of these cumulants. All are proportional to square root of time t. It means that the CGF itself is proportional to square root of time t. So now we are interested in the correlations between the tracer position and the occupation of the bath. Naturally, we introduce the joint process xt and eta at a position xt plus r. In other words, we are doing things in the frame of the tracer. We have now two random variables. We introduce two conjugated parameters to define a joint cumulant generating function. So by definition, this is this quantity. First point, because eta is an occupation number equal to 0 or 1, you can rewrite exactly this quantity as follows. So it involves the CGF of the only tracer, and this quantity, W, which will be the main topic of my talk. So W is defined this way. This is the average of the product of the occupation number times exponential lambda xt divided by the CGF of the tracer. Not the CGF, but the exponential of lambda xt average. I will call it the generalized density profile generating function. You can expand it as a function of the conjugated parameter. It will define what I will call the joint cumulants. So just to understand what they are, let us have a look at the first ones. So for n equal to 0, we only have the average of eta, and because we start from the equilibrium condition, it is equal to a constant at all times. It does not carry any information. Next cumulant, the first one, it can be rewritten as this covariance between eta and x. In other words, it provides a measure of the correlations between the TP displacement and the occupation of this site. The next one can also be written as a covariance, this time between eta and xt to the square. It provides a measure of the correlation, this time of the fluctuations of the TP displacement and the occupation of a site. Finally, these quantities do exactly what we want. They quantify these correlations in the joint process. Last point, as we did for the tracer position, it is interesting to consider the scaling of these quantities. And from numerical simulations, and consistently with what I'm going to say later, you find this scaling for W. At large time and large space, it involves only this combination of space and time, which is a diffusive combination. This is a non-trivial aspect. It means in particular that the profiles are not stationary in the frame of the tracer. They constantly evolve with time. And there is a scaling function. I will call it phi in what follows. In the frame of the tracer, because we are in the frame of the tracer, you find that phi does not converge to a constant function of r. It involves this combination of space and time in the reduced variable. It means that the profiles are not stationary. Okay? And this scaling typically is at the very origin of the scaling of the CGF of the tracer. In some sense, it provides the mechanisms leading to the anomalous diffusion in single-file diffusion. Yes? It holds for arbitrary density. Okay, so finally, to sum up this quite technical slide, the GDP are key quantities. First, they give access to the Bath tracer correlations, as I've just shown you. And second, as I will show you in the next slide, they control the time evolution of the only tracer. So, yeah, this is an infinite system. I'm considering only, excuse me if it was not clear, from the very beginning, I consider only an infinite system. Situation is radically different, of course, for a finite system. Yeah, absolutely, but you do not have anomalous diffusion in this case at long time. Okay, so this is, all these concern infinite systems. So in what follows, I will focus on these key objects. So a word about the microscopic equation describing the system. So you can obtain an evolution equation for these key quantities I just introduced by starting from the mass equation describing the full system. But as usual in this case, they involve higher order correlation functions that involve here two occupation numbers. And this is the usual situation. You're facing an infinite hierarchy of coupled equations. This equation can be written this way, so it couples with these higher order correlation functions. I don't want to go too much into the detail, just want to say that you can introduce new correlation functions by subtracting essentially a kind of mean field contribution, and it allows you to write the bulk equation in a quite compact way, but not very useful at this stage. You can understand the meaning of the first terms. Here you have a diffusive contribution because the bulk particles execute symmetric random walks. You have a kind of drift term with the first derivative here because you are in the frame of the tracer. Actually, B nu can be shown to be proportional to the derivative of the CGF of the tracer. This is a kind of generalized velocity. And all the complexity lies in the last term because it couples to higher correlation functions. This is a bulk equation. It has to be completed with boundary conditions, both close to the tracer and at infinity. Close to the tracer, you have similar expressions, similar conditions, which also couple to higher correlation functions. At infinity, the situation is very simple because eta and x decouple, and you finally end up with a simple condition at infinity. So this tells you how the presence of the tracer affects the repartition of the Bath particles around the tracer. These are the density profiles. In turn, you can be interested in the reverse question, how the reorganization of the Bath particles affects the motion of the tracer, and the answer is provided by the time evolution of the CGF psi. You can obtain this exact expression that tells you that dt of psi is controlled by the profile just in front and past the tracer, a fact we announced on the previous slide. So these are the microscopic equations, and as in this case is a rule, they are not closed. So first step, to say something, we go to the hydrodynamic limit. So we use the scaling forms I discussed previously. Psi is proportional to square root of time t. W has this scaling we discussed previously. And you need more. Actually, you need also the scaling of this guy which describes the higher correlation functions. And this is a technical point, but actually you need the two first terms of the expansions, not only the leading one. But if you use that, you can show that the mass equation for the full process leads to the following expression. So again, the double derivative comes from the diffusive motion of the buff particles. The v phi prime comes from the time derivative in the mass equation. The b nu phi prime is the drift term we mentioned previously, but all the complexity is in this c term, which involves these two functions that describes the higher correlation functions. This is not closed. Concerning the boundary conditions, you have a first interesting result, I think. The first boundary condition against the tracer, close to the tracer, is automatically closed in this hydrodynamic limit. It involves only phi prime, phi, and psi. So first result. Second point, this was already clear at microscopic level, so you keep the same boundary condition at infinity. And finally, you write what I would call the cancellation of the generalized velocity. You have that d psi over dt, because psi behaves like square over t, tends to 0 when t goes to infinity. If you now plug this in the expression I gave previously at the microscopic level, it gives you an equation that relates the profile past the tracer and the profile in front of the tracer. So these three equations framed in red are important. The last one is nice, but not very useful at this stage because it is not close, not very useful at this stage. The question now, how to go further and obtain explicit results. Our strategy has been to consider first specific situations, as for tracer diffusion, the dense and the dilute limits, and I will after present the general case. So let us start with the dense limit. Again, this is by far the simplest of the situations. Actually, in this case, phi minus rho can be shown to cancel like 1 minus rho, so you can construct this rescaled density profile. And the key point is that the unknown terms that involve higher correlation functions typically behave like 1 minus rho to the square. This is easily checked by the very definition of C that involves products of occupation numbers. So finally, in this case, the situation is simple. You have a closed differential equations satisfied by the density profiles. You can solve it, of course, use the boundary condition I described previously. You can even compare the cumulants you can deduce from this expression as a function of the rescaled parameter we introduced previously. This is a plot that compares with numerical simulation for the three first cumulants, and as expected, of course it works when rho is high enough. As a remark, I told you, you can obtain as a byproduct the cumulants of the tracer position, and you retrieve the non-exact results obtained in 2013 by completely different methods. So finally, in the dense case, it is easy to obtain a closed equation satisfied by phi, and this is a linear differential equation. Second limit, what happens in the dilute limit? This dilute limit corresponds to rho going to 0, and you have to keep constant, actually, these space and time reduced variables. Again, this dilute limit of the SEP is interesting by itself, but also because it corresponds to the model of hot point-like Brownian particles on a continuous line. This time, C of V, the complicated term coupling to higher correlation functions, is not negligible anymore. So we have to do something. And what we did is to propose a self-consistent closure relation to calculate C of V. And I claim that this closure relation leads to exact results in this dilute limit. I will explain why in the next slide. If you use this closure relation, you actually obtain a very simple closed equation satisfied by the GDP generating function. And this equation is the following. This is, again, a very simple differential linear equation satisfied by phi, but there is a non-trivial parameter, which is what I call psi, which is the derivative of the CGF of the tracer rescaled by time with respect to the conjugated parameter lambda. And I claim, I will tell you why at the next slide, that this equation is exact in the dilute limit. You can solve it, of course. It involves what I call beta, the ratio between psi and lambda. And if now you write the cancellation of the velocity, which happens in front and past the tracer, you obtain this equation, which can be seen as an implicit equation that allows one to determine the cumulance of the tracer position. I would like now to comment on these results. So you obtain this cumulance, and actually you retrieve the exact cumulance calculated in the dilute limit in this series of work. In other words, it validates self-consistently our Creuser relation. Second point, you have more. You have the explicit expression of the GDPs at arbitrary order in this dilute limit. For instance, you have phi 2, you have phi 3, and etc., etc. Interestingly, these GDPs display non-monotonic behavior with the distance. You can plot them, and this is again a plot of this cumulance as a function of the rescale variable v. And as you can see, for n equal to 2, n equal to 3, they are non-monotonic, which is not, I think, a clear thing. Last point, you can show that this GDP actually coincides with the saddle point solution that is obtained the formalism of the macroscopic fluctuation theory obtained in this work if you take them at a specific point. And this provides a further validation of the expression we obtain. But the key point here that these profiles, they satisfy a very simple closed differential linear equation. Question now, what can be said at arbitrary density? So I just would like to try to give you the strategy we try to follow to say something. So our guess is that there exists a closed equation. And this closed equation has the same form as the one we started from in the dense and the dilute limits. So we suppose that this operator, defining on the left-hand side, still plays a role in at arbitrary density. So we have some constraints on the right-hand side. We know, of course, that it goes to 0 when rho goes to 0 and rho goes to 1, because psi here goes to 0 in the dense limits. An important point is that you can, for instance, determine the left-hand side at order lambda, and you find 0 for the right-hand side at any density. This is easy to check. So it means that the right-hand side is a big O of lambda square. In other words, technically, it acts as a kind of source term in an expansion as a function of lambda. And it was at the origin of what we did. So we try, by relying on the previous remark with a link with MFT, to compute the first order of 5 up to third order, use the MFT to do that, and see the structure of the right-hand side up to this third order. From this, we infer the general structure, and finally, resum the series in lambda. You obtain something which is very ugly, but by a series of transformations, you finally obtain a simple closed equation, and I would like to discuss. It turned out that the two functions that I call capital omega, which are basically rescaled derivatives of the profiles, they're proportional to phi prime, but they are rescaled. These two quantities are entirely determined by a closed linear integral equation, and this equation is actually a Wiener-Hopf equation with a Gaussian kernel. So the unknown is capital omega. We have this psi parameter that we already defined. We got the intuition from this quantity from the analysis in the dilute limit. This is d psi divided by d lambda. And here, the small parameter omega is actually determined by the boundary conditions that come from the very definition of omega. Capital omega in 0 is equal to plus or minus 2 psi. So omega is parameterized by psi. And I claim that this closed equation is exact, and again, I will tell you why after. You can solve, just a remark, about these Wiener-Hopf equations, as discussed yesterday, they are involved in a variety of situations. For instance, they are involved in the context of the persistence of gem processes, very nicely reviewed in this review by Satya and Gregory. They are also involved, as we heard yesterday, for instance, in the context of the Capesi equations. We heard it in the talk by Pierre de Dussal yesterday. So you can solve this linear equation, and you obtain finally this expression for the semi-Fourier transform of omega. And from this expression, you retrieve many results. First point, you retrieve the CGF obtained in the exact works by Imamura, Malik, and Sasimoto. You can retrieve all the cumulants. The fourth one I discussed previously, but also the sixth one. All this is not new. It was contained in the work by Imamura, Malik, and Sasimoto, but they are obtained from an exact microscopic approach. So this is, I think, the first validation of the exactness of the Wiener-Hopf equation I presented before. You have more. You have now the complete structure of the problem. You can determine, for instance, phi 2, the second cumulant, phi 3. These quantities we determined previously only in the dense and in the dilute limits. You obtain them for any density. This is a comparison of this expression with the result of numerical simulations for the first, the third, and here the second joint cumulants. And as you can see, you have interesting changes of behavior as a function of the density. Last point, as I said, the MFT can also be used to determine perturbatively the first coefficient phi n. We try to determine them up to order 5, and up to order 5, they coincide with those obtained by our approach. I think this is a second validation of the exactness of the Wiener-Hopf equation. I will provide other arguments in favor of this exactness, but first, I will give you some extensions of these results. The first step of extension, you can extend these results partially to out of equilibrium situations. You can consider the case of an initial step of density where rho minus is different from rho plus, which is a paradigmatic setup because it remains transient at all times. Actually, the closed equation I described previously still applies in this case, and you just have to modify the boundary conditions at infinity by trivial replacements. If you do that, you retrieve the non-exact cumulant generating function obtained by Imamura, Malik, and Sasimoto, also in this case of an initial step of density. Again, you have more. You have the complete spatial structure of the Bass-Tracer correlations. This is again the comparison with numerical simulations. So first extension, you can extend in part to out of equilibrium situations. Second extension, you can consider other observables than tracer diffusion. You can also consider the case of the integrated current through the origin up to time t. We already heard about it. So this is the number of particles that cross 0 from the left to the right, minus the contribution coming from the right to the left up to time t. And this is another important observable of single file transport. Actually, the closed equation I described previously still applies in this case, with the only condition that you replace psi to 0. If you do that and slightly modify the boundary conditions, but you can infer them from the microscopic situation, if you do that, you retrieve the known exact CGF of the current obtained by Derrida and Gershenfeld by relying on the beta ansatz. You have more? Yes, annealed case. This is the annealed case. Okay. All here is in the annealed situation. So you have also the complete spatial structure, but this time it concerns the Bass flex correlations. This is the comparisons with numerical simulations. So second type of extension, you can in principle obtain other observables. Last type of extension I wanted to mention, extension to other single file systems. So this is very modest extension up to now, but I would like to present it however. I would like to remind you that a single file system can be described at large scale by two quantities. First, so-called diffusivity D and the mobility sigma. They can be defined by considering a finite system, this time, in contact with two reservoirs, rho L and rho R, and you can be interested in the number qt of particles transferred from the left to the right up to time t. So first situation, let us consider rho L and rho R, different but close. You consider the average of qt, rescaled by t, take the limit t large, and you define d this way. Second situation, this time rho L is taken equal to rho R, qt in average is equal to 0, but you can consider the second moment, rescaled by time, and you define this time the mobility. We heard about it yesterday. In the case of the SEP, d is equal to 1/2, and sigma is a quadratic function of rho. Actually, what I said previously can be extended to the case of d still a constant, and sigma a general quadratic function which is equal to 0 when rho is equal to 0. It covers, for instance, the KMP model we heard about yesterday. In this case, the closed equation becomes the following. You replace this term by this general expression. So this is a modest extension. We do not claim to describe all single file systems, only this type of system. An important example of application, I think, concerns the tracer diffusion in the random average process that has been studied a lot, for example, by David and Satya. I remind you the definition of this process. So this time, this is on a continuous line, not a discrete system anymore. And you assume that at exponential times, particles on this line jump in either direction to a random fraction of the distance to the next particle. This system is not described by d constant and sigma quadratic, but you can map it on a system that is described by these conditions. And finally, you can obtain results for tracer diffusion in the RAP. I just would like to conclude by coming back to this important question of this exactness of the closed Wiener-Hopf equation. I just would like to recapitulate all the arguments in favor of it. First, we have compared with exact expressions of the CGF of first tracer position and second the integrated current, and both actually are contained in our approach, including in the case of an initial step of density. Second point, you can also compare with MST. First, perturbatively, and you retrieve the coefficients up to order 5 with those obtained by this method. You can also do it non-perturbatively. We did it numerically, because we are not able to solve the MFT equations, and we can find an excellent agreement with our analytical solution. Since there has been an important work done by Malik, Moria, and Sasamoto, relying also on the method developed by Pierre Kragenbrink, and they prove that this equation actually holds true by relying on this MFT. This is done in the case of the current in the SEP. So finally, we claim that these Wiener-Hopf equations are exact. So to conclude, we have discussed the Bath tracer spatial correlations in the SEP, and we have tried to show that they can be determined analytically. These Bath tracer correlations, I think, are physically important, but also are key tools to analyze and maybe reanalyze single-file diffusion because they satisfy a strikingly simple closed equation. In particular, they allow you to retrieve very easily all known results on the cumulance of the tracer position. Importantly, this very same equation applies to a variety of situations involving single-file transport, including the case of out of equilibrium situations, at least some of them. It allows you to describe other observables than tracer position and potentially other single-file systems than the SEP. And I think that all this points towards the generality of this equation. I just would like to conclude by thanking again my collaborators and by thanking you for your attention.